Hello everyone. We are starting free open lectures in Discord, all lectures held weekly without interruptions. If you, the viewer, want to ask questions and receive answers in an online format, join our lectures. The link to Discord can be found in our Telegram channel. To find out the schedule for the lectures, join our Telegram channel and stay updated with the latest news and announcements. Plus, to calculate the result, you need to first press the button to multiply the value by the total number of possible combinations that we have chosen from the options available behind, and it will result in a value of 2k plus 1 minus the mech, and minus the result of the operation of mech multiplied by the variable mech minus 1 minus k here. Here will be yes and definitely, laughter minus 1 definitely. Interestingly enough, we have two such cases, and accordingly, the question arises about where the dynamic programming, or DP, comes into play. Besides the fact that we are iterating over k, the essence is simply that we need to find the number of possible combinations. We can't rely on built-in libraries here, because each one searches in linear time, so we will have to build a Pascal's triangle based on the scale that will find the number of combinations. This will be constructed in quadratic time, meaning we pass information from the top to the two below. Then we pass such information. Here, a 6 should be in the middle of the TFSP, or the triangle's face structure pattern. Accordingly, this structure is built, and then we obtain such a result using the formula k less than half, and after 7 mech, we just iterate in such an interval. Otherwise, we have...
Want to become a great programmer? Subscribe to our Telegram channel.
That's one option. Just add yourself, and we move on. Are there any questions about this problem, about the solution? So this problem is more about the commentary, but it can't be solved without DP either, due to the huge number of computations and combinations and permutations. So, does anyone want to code? Remember the troubles of Newton? How it's calculated? The forums themselves are not complicated. Just remember this table at least, and that's it. We will be gathering the basics, and there will be a second task as well. Such basics.
The main point is that if we have 2k less than n, we will have a mechanism between k plus 1 and 2k plus 1 because it cannot be less than the overall length of our subset, but it will definitely be less than 2k plus 1. Is that clear? K plus 1 is our permutation. As you can see, in this particular case, there are no other numerical digits. So, what exactly is the maximum value of k for us in this context that we are considering currently? K, well, it will be less than half of n, always. Well, in this case, in one case, here it is. That is, if we have k greater than half of n, then we will have such an answer. We will just simply write it like this, indeed right away. In one particular case, we will have an arrangement or permutation of mechanisms in such a wide range. Accordingly, if we choose a specific or certain mechanism that we have chosen, there will be some individual elements that we need to select carefully in the subset that we have strategically placed. They can be either on the left side or the right side of the arrangement. On the left, we will need to carefully select the value of TFSP, which results in a total of 2k plus 1 minus the mechanism, which provides us with the exact number of elements from n minus the mechanism from the entire remaining end. We need to carefully select 2k plus 1 minus the mechanism from the front portion, while from the remaining part, we will need to carefully select from the mechanism minus 1 in length, which will be the remaining first part of the elements that we placed in the subset. Accordingly, the remaining individual elements that we, so to speak, did not place either here in the front or there in the back will be either at the front, which will be the first few mechanisms in sequential order, or at the back end, which will simply be after the current specific mechanism in the sequence. Is that clear to everyone? So, accordingly, yes, this will be the form. We will permute all this combination on the mechanism. But what is this? What are we actually selecting? Where we specifically choose, here we are iterating through the mechanism, which is defined by our function. That is, we choose that it can be like this and count the number of ways to obtain the Domke parallelizer. How many subsets will there be such that the mechanism is right here? Yes, that the mechanism is right here, and the length of the subset will be equal to k. So how exactly will we count in this case? So, we choose those elements from the subset that are greater than fir, and those that will be less than fir. The ones that are greater will be in the quantity of 2k plus 1 minus I, and the total number of elements on the right will be n minus fir. Accordingly, the number of combinations has increased. On the left, we will have a total of fir minus 1 elements, which will be TFSP, because fir itself is an index, and we need to choose from fir minus 1 minus k. Why minus k? Because k is the same there. Fir is the length. By count, which is the length of the permutation, that is, k plus 1. So, minus k means that out of these elements on the right, k elements will be the first firs by count. We need the third fir by count, the fourth, the fifth, right? The fifth type. Yes, yes, yes. Here is k plus 1 fir, and here are the first k firs. They will be lying somewhere around here, and we don't need them, so they won't be included. Therefore, there won't be any firs on the left because we selected that bunch. Well, yes, look, we have a permutation, which in this context refers to a specific arrangement or sequence of elements, and we have some firs, which are important for our collection. We need to get the sixth fir, which is crucial because it completes our set, and depending on where the other elements will be located, which are 2, 5, 8, and 9, they will all be there, positioned strategically to maximize their impact. There are 5 of them, each playing a unique role in the overall arrangement. Yes, like k, like k. Accordingly, we subtracted them. Do we need k plus 1 fir? Yes, we need k plus 1, so minus k is strictly subtracted. That's when I understood. Yes, we kind of can't use them because they are sort of inside the current ones, right? They have entered. And we take from there and place new ones at the end. This is the number of combinations, if you understood everything. All right, I got it. I can turn off the transformation. Call me when you understand everything. Well, go ahead, give it a try. For now, just write the matrix from the number of combinations. A matrix of combinations? Pascal's triangle or something? Yes, that one. There will be a multitude of too many combinations, so built-in tools cannot really be used. Damn, I'm looking at the guys' goats who were sisting. They are the Pascal triangle, apparently, where they know. And what did they do? They did.
Well, they actually concentrated on factorials over factorials, right? And indeed, they go there for that, since a formula is needed for the reciprocal number, isn't it? Well, when we talk about modulus, we need the inverse formula for division, the inverse number. I got it. And they didn't know about him. They were using binary medieval exponent and multiplication. I'm looking at this. I'm looking at this. Well, that's how it certainly happens. And here it will all just be fashionable. It's happening. So here we have Alice and Bob, as you might expect, our usual characters. They are playing a game, this time a very delicious one indeed, and they are eating cakes. Each cake has a level of deliciousness, and they eat them in turns. Meanwhile, Bob eats absolutely everything indiscriminately, while Alice has rules. She must eat an absolutely incredibly delicious cake that is more delicious than any she has tried before. And indeed, accordingly, Alice really wants to eat as many delicious cakes as possible, while Bob truly wants her to eat as few of those cakes as possible, definitely. And accordingly, in the optimal game, it is necessary to find out how many cakes Alice will eat. In terms of quantity, not in terms of deliciousness, but simply the number of cakes, TFSP. We have a limit here again of 5,000 in total, and the answer is simply how many cakes a person will eat. Accordingly, if I break down the tests a bit, we will see what will happen. Let's take the simplest case. It will explain everything. This is 1, 4, 2, 3. It is quite evident that something needs to be forgotten. We have 1, 4, and 3, which means the deliciousness of the cakes can be sorted immediately. Accordingly, we will explain in this test how Alice eats and how Bob eats. Alice's task is essentially, in this context, to eat the cheapest cake that she hasn't eaten before. So she starts with the 1, then if there is a 2 left, she eats that, then the 3, and she continues until, so to speak, there is something left to eat. Very simple and straightforward. Bob, who is always strategic, eats in such a calculated and deliberate manner that Alice's carefully curated selection of unique and exquisitely delicious cakes is minimized to the greatest extent possible. That is, there are repeated treats, meaning that array A can consist of repeating elements, which is quite common in many scenarios where datasets have duplicates. This is a common occurrence in many datasets where duplicates are present, and it is important to handle them appropriately. Here, one trunk is the most sour, which fits perfectly into our criteria for sorting, so we will sort it in ascending order to make it easier to analyze. In this particular case, the trunk that is most sour fits perfectly into our criteria for sorting, which is why we will sort it in ascending order. What we get after sorting is 2, 3, 3, 5, 5, 6, 6, 8. However, I initially missed the number 7, so let us include it in the sequence, resulting in 7, 8. Additionally, there are 2 pairs of drumsticks remaining, which are crucial for our final analysis and understanding of the dataset. It seems that's everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I didn't miss anything. And globally, we have 7 types of cakes. 1, 2, 3, 4, 5, 6, and 7, each representing a unique category in our dataset, which is essential for understanding the overall distribution. This categorization is essential for understanding the overall distribution and characteristics of the dataset. And Bob's task is to reduce the number of types of cakes. So, in this particular scenario, for example, when Alice eats the second cake, Bob specifically eats, let's say, the 8th one, which is definitely advantageous to eat. It is important to note that in this specific game, this strategy is beneficial. As a result, Alice continues by eating the 3rd cake, and the entire type is eliminated. Bob eats the 7th cake, and he also completely eliminates the entire type. Alice, feeling quite hungry, eagerly eats the 6th cake, savoring every bite of the 6th, then moves on to the 5th, enjoying the 5th cake. He is completely eliminated like this. And Bob is trying, well, for example, this whistle. It actually won't change anything. This whistle. Alice is eating this one.
Want to become a great programmer? Subscribe to our Telegram channel.